Hello, this is section 5.4 for Calc survey, and we're going to be talking about interpretations of the definite integral. So it's an application section, awesome practice, and it's a great way for you to fully grasp the meaning and the purpose and the usefulness of definite integrals. So just a quick review, the notation for a definite integral, remember it's the integral from a to b of f of x dx. It's the area under this function to the x-axis. And if that function dips below, then it's going to come up to the x-axis from a to b. All right, and remember the area above is represented as a positive area, and the area below, it's not a negative area. We can't have negative area, but we represent that area by putting a negative symbol in front. Okay. And just remember that this has come from finding infinitely many rectangles under that curve. Okay, that's where that notation came from. All right, if f of x is velocity in miles per hour and x is time in hours, then the integral has the units miles per hour times hours. So, and if you look, f of x, so let's say that was your velocity function in miles per hour, dx is the change in time, so that would be hours. So you can see how by multiplying these, that's what it's showing you here, the hours cancel and you're left with the number of miles during that interval. Okay, so if you ever get confused with the units, go back to here and make sure that it lines up and you can see how it cancels nicely. Okay, sometimes the integrand, the function inside the integral, is stated as f prime of t, and other times it's just f of t. Regardless, the integral is the area under the curve. And I've said this multiple times throughout the last couple of videos. Don't get caught up with this having to have the tick mark there. And it doesn't necessarily have to be a derivative. This could be a second derivative. You don't know what's going on. You're just trusting that this is the function. You're finding the area under from a to b. Okay. So units of measure for a definite integral, we've kind of talked about this. The units of measurement for this definite integral is the product of the units for f of x and the units for x. So that's just your f of x and then the change in x. Meaning of the definite integral, f of t is the rate of change of quantity, if, big if there, sorry. Then this is going to calculate the total change in quantity between a and b. All right, so here we go. Let's try an example. A city has a population of 36,000 people. Over the next 5 years, the population grows at a rate determined by the model. Okay, and we're growing in thousands of people per year. That's what this is in terms of. So give a definite integral that represents the total change in population over the 5-year period. So there's my integral from 0 to 5 of our derivative, 1.3 to the t dt. Remember, if ever there's an integral symbol, there has to be a dx, dt, something. There has to be a what's the change in terms of. All right, and then we just put this in our calculator. We're going to learn how to solve this by hand in the next chapter. That's coming. But for now, you just put this in your calculator. It spits out the answer, and then you'll see this is in terms of thousands per year times the change in years. Years cancel, you're left with thousands of people. Okay. All right, find the population after the 5-year period. So this is how much was, now it's positive, so it was added over that 5-year period. So now you're going to take that initial amount you started with at year 0, 36,000, plus your 10,340, add that together, and that's how many people you have after 5 years. All right, here's some visuals for our next problem. So I'm not even going to try to pronounce that. The brothers, these brothers, were 18th century pioneers in the field of hot air ballooning. The graph from one of their early experiments shows the balloon's vertical velocity in feet per minute with upward velocity as positive. So here's your upward velocity here. And then now they're going. So this is when they're going up and now they're going down. So over what intervals was the acceleration positive and when was it negative? So you're looking at the derivative graph here, feet per minute. So when we're talking about acceleration, that's the derivative of the derivative. So if I want to know when acceleration is positive, that's when the slopes of the tangent lines are positive, or when acceleration is increasing. Okay, So our acceleration is going to be positive at these intervals that my derivative is increasing. And then my acceleration is negative, so the slopes of the tangent lines are negative when the acceleration, or when our velocity function's decreasing. Right? That's a little confusing, but let me know if that doesn't make sense. At what time was the greatest altitude achieved and what was it? So you have to realize it's really tempting to stop it here at 40, roughly 40, but technically you're still going up all the way until you get to that x-intercept there, okay? So that's why it's 42.5. And then it wants to know what's the greatest altitude. So we went ahead and counted the squares, got roughly 23 squares, multiplied that by the area of each square. Notice the area of each square is a 5 by 5, so 25, and that's how we're getting our distance. This particular flight ended on top of a hill. How can you tell from the graph, and what was the height of the hill above the starting height? So you can tell because you can clearly see the area above is greater than the area below. All right, so again, we counted the squares and we counted roughly 8 squares below. So we took the height we had achieved above and then subtracted the area below and got 375 feet. So just a fun little applications problem. Okay, let's try one more here. I'm going to move me up here. All right, a bicyclist is pedaling along a straight road for 1 hour with a velocity v shown in the graph. So again, we're looking at our velocity function here. She starts out 5 kilometers from the lake, so keep a mental note of that. And positive velocities take her towards the lake. So here's where she's going towards the lake. Here's where she's going away from the lake. So does the cyclist ever turn around? If so, at what times? And again, this is really tempting to say, oh, it's here at the maximum and the minimum, but that's not true. It's going to be where, because notice these are all towards the lake. So maybe she's speeding up and then she starts, you can't just turn around when you're going the fastest. So she has to slow down. Now she can actually turn around and go away from the lake. So at 20 is where she makes a turn. When is she going the fastest? How fast is she going then toward or away from the lake? Okay, so her speed here was 10 kilometers per hour towards the lake, but then over here she's going 25 miles or kilometers per hour away from the lake. So that's actually her fastest rate right there. So I said at 40 minutes because it is 25 kilometers per hour away from the lake. All right, when is she closest to the lake? Approximately how close to the lake does she actually get? So realize, don't forget that she started 5 kilometers away from the lake. So that's going to be important here in a minute. So if she's going towards, so she starts here and she's going towards the lake until she gets to roughly 20 minutes. That's the closest she's going to get because the rest of the graph, she's going away from the lake. So that's why I said around 20 minutes. And then I went ahead and made the notation. So the integral from 0 to 20 of v of t dt, that's the mathematical notation. This means the area under this curve from 0 to 20. And then I just roughly counted the boxes. Okay. So I counted roughly 3 squares. And please make note that it's a 5 by 10. So you have to be careful there. But also, did you notice that you are in kilometers per hour, but over here it's in minutes? Lovely. So that's what I'm doing over here. I'm converting the notation. So I converted the minutes into hours. And so that 10 minutes right there. So this is me finding the area of each square to multiply it by 3. But I converted that to hours. So you end up getting, that's where that 2.5 kilometers is coming from. Right? So I had to convert those minutes to hours so that I could get the area of one individual square. That's what this is, 5 over 6, when you multiply those. And then multiply that by 3 to get the area under that curve. So then I took the 5 that we had started, that's where we had started, and subtracted because we went towards the lake. So now we're roughly 2.5 kilometers away from the lake, or closer to the lake, I should say. All right. When is she the farthest from the lake? Approximately how far from the lake is she then? So I said definitely 60 minutes is when she's going to be the farthest. Counted those squares, did the whole area again. I know it kind of got cut off there, but you should be able to see that in Canvas. And then from there, just subtracted. We had the 5 minus the 2.5. So this is where we started, minus because she went towards, and now we're adding 10 because now she's going away again. And then that answer is below here. But just make sure you include units in your answer. Okay, so rethink through some of these examples. Definitely do your homework. You have to practice doing this stuff, okay? And understanding how to answer what it's asking for and how to use the graph and being really careful with your units. And really the units will help you with a lot of these problems, keeping straight what you're trying to calculate, okay? All right, well, please do your homework and let me know if you have any questions.